Alright, Chapter 5, Thermal Capacity of the Freight Car Wheels. Introduction. Thermal capacity of freight car wheels represent with one of the major design criteria that must be taken into account. Air brake system design, either the design braking level that must be limited to thermal capacity not exceed either the normal or abnormal operation condition for the braking effort must be achieved by augmentating tread braking with other forms of braking. The various forms research several attempts have been made, especially within the past 20 years, to determine the actual thermal capacity of the freight car wheel that typically found on surfaces in North America. These research has included experimental or theoretical approach to the particular branch that has been made with wheel diameters that perform various kinds of experiments. Investigation of thermal capacity of the freight car wheels. Purpose of this section summary to discuss the most significant portion of the research activity present collective assessment of the thermal capacity of the freight car wheels. 5.2 parameters consider the perform they may variation found with the freight train brake and equipment, the train operation, other factors. The wheel thermal capacity must be evaluated with respect to many of the parameters of the activity. Parameters include the following: cyclic versus drag braking, wheel diameter, size and shape, wheel material, heat treatment, and the worn versus non-worn versus new wheels, brake shoe material, show alignment, and other consideration. Each of these topics discussed in the following in terms of the research efforts performed in the recent years. Cycle versus dragging braking. The thermal capacity will depend on the type of the operation on which the wheel experience the serve of the term of the freight serve of the cycle braking is due to the engine and control of the train slack action when operating long trains over undulating train. Although brake levels due to the type of the braking, also called the stretch braking, are normally not large if the wheels are exposed to the alternate cycle, the heating and the cooling. Another form of the braking that can be considered the all-cyclic braking, the full surface or emergency brake application used in the engine managed to produce the large change in the train speed. For the example of 50 miles an hour to a stop, engine with the wheel tread temperature increases at a high value with a short period of time, and then drops back to the ambient level and rate determined the ambient condition. The other type of the freight train brake operation referred to the drag brake is normally associated with a steady brake of the application over a long period of time. Typically occurs when the train is being operated down a long steep grade where the train brakes are applied with the balance of gravitational force of the grade. 521 safe thermal load. The research project sponsored by the Griffin Wheel Company. Safe thermal load was defined. The thermal load which does not produce the elastic is a formation in the wheel. Went and Camp and Kip, 1975, page 2. An elastic deformation proceeds to produce and surface recover the braking and manifestation of residual stress in the wheel caused by a large variation of the temperature between the wheel tread surface of the other portion of the wheel. The variation of the temperature, referred to as thermal gradient, is believed by some of the investigators to be more significant in the cause of the wheel residual stress, the equivalent or higher, even higher with the head tread temperature sustained for a long period of time. In other words, the thermal shock of the effect of the cycle braking consider this more. Some of the research too more destructive to the wheel than the slowly applied uniform high temperature brake application followed by a slow cooling process. To place the thermal capacity of the wheels in perspective, respect of the cycling and dragging braking application, the braking level of both types of the application must be known. For example, the high level of the dragging braking could theoretically exist as in which the high wheel temperature would reach at the destructive level, assuming brake shoes would not be disintegrated, the wheel would fail with the amount of the cycling braking may not be a factor. 5212 recent test method and test conducted at the University of Illinois. Several type of the wheel braking level of the cycle of the investigated use the wheel diameter of the residual stroke of the wheel is measured after subjection of the wheel various braking level to measuring the opening of the solve of the cuts of the made into the wheel rims after testing. The result of these tests are shown in figure 5.1. Opening 10 inches, depth of the cut inches. Wheel strength expressed in the terms of the saw cutting opening option after exposure various car brake levels. Researchers have made with the following conclusions concerning the results shown in figure 5.1. Went and Camp with the 1975, page 15. Starting with the given wheel design, heat with the treatment, the parent with the more of the center rear with the brake applicator with the greater opening of the wheel. Upon performing the radial saw cut, the result would imply that the most severe load of the series was the 100 horsepower test for 15 minutes of the type of the test with virtually consuming the new composition shoe. The one test could possibly be experienced in surface with the stuck brake of the substantial more severe braking cycle. The surface is difficult to imagine. Wheel subject to this thermal load fracture for the radial saw. The cut progressed through the rim. None of these other wheels fractured upon the sawing. For the unfortunately limited data, they have the rather well-defined dividing point for the present and would be seen to the thermal loads of the producing substantial less saw cut openings from the wheel had fractured upon sawing should be reasonably safe. It should be noted for the above mentioned case of the 100 horsepower 15 minutes wheel did not fracture until the saw cut was made. The tread temperature reached 1,146 degrees Fahrenheit. Went Camp Kip 1975 table 1 new composition brake show was consumed during the test. How the wheel would solve the combined physical loads of the repeated thermal cycle. The actual train operation could be summarized. Wheel geometry, size, and shape. Wheel size, diameter with the shape of the cross section of the additional factor for the effect of the wheel thermal capacity. Both of these factors are discussed below. Alright, 522 wheel side with them research performed with the Westinghouse of the air brake company using the full scale of the dual wheel diameter of the any investigation of the made with the tread temperature of that would be produced with the various side of the wheels of the given level of horsepower dissipating during braking cable 1973 following diameters type of the Class B wrought steel warrants were tested in both the new tread and worn tread condition 40-inch multi-wear 36-inch multi-wear 36 and 3/3-inch multi-wear 36-inch one-wear 28-inch multi-wear 28-inch one-wear. The result of the test presented in the figure 5.2 the new wheel, the wheel tread temperatures, new wheels nominal 28 to 40 inches wheel diameter inches. The conclusion made with the test results were as follows. The cable of 1972. If the brake horsepower per the wheel increased, the temperature arrived at the given wheel with the creep the same length of the time as the nominal wheel diameter. If the degree of the temperature rise of the wheel increased, as the actual wheel diameter due to the wear with the degree of the temperature arrived at the wheel will increase, the approximate range of the temperature through the wheel with this change of the curve versus the nominal wheel diameter approximately a straight line. Maximum wheel tread temperature of that wheel can stand without problem to determine the allowable brake horsepower of the wheel, therefore the grade braking operation. Wheel shape of the efficiency, the thermal strength of the property for the tread braking combined with the physical strength of the property for the vertical lateral loading have been investigated by performing analytical stress analysis of the Novak Etel Al 1975. This research was performed in part to explain the difference in the wheel plate surface failures of 28-inch wheels with straight and curved cross sections on using two-dimension with a finite difference of the finite element mathematical method for the calculating over the octahedral shear stress of the 28-inch straight plate B28 and the curved plate CB28 wheel well evaluated under the surface load application for the vertical lateral wheel loads with flange throat with a combination of the emergency brake application for the load applications are shown schematically in figure 5.3. Shows the wheel rail load plane rail brakes shoe plane 180 degrees. Coordination system load application reference plans for the analysis of the wheel stress. Surface loads applied were as follows. Car wheel rail contact loading vertical 46,100 pounds, lateral 20,000 pounds. Tread brake loading, brake shoe force 62,100 pounds, tractor force 7,200 720 pounds. Thermal load, particular thermal load applied with the wheel corresponding with the temperature distribution and wheel after 55 seconds of the brake application when treaded. Surface temperature, whether at maximum of the temperature field of the braking at any time interval shown figure 5.4 and 5.5. Straight plate wheel thermal loading figure 5.4. Curved plate wheel thermal loading. Novak E10 1975 used the furniture of the copyright owner. Alright, maximum octahedral head stress is calculated where with the describe of the authors as follows. The maximum octahedral shear stress produced the adjacent of the front hub fillet over the straight plate with the wheel with a slowed application that's significantly higher than stress generated only rolling loads, vertical lateral wheel loads. This maximum stress occurred with approximately 45 degree in wheel rotation. The dimension of the wheel rotated with 180 degrees to position the maximum octahedral stress intensity of the about 13,500 psi near the back of the rim fillet. Also occurred with after 45 degrees of the wheel rotation diminished as the wheel traveled over perhaps reaches 180 degrees. Author noted the previous work has found with the mechanical wheel rail contact loads comparable to flows. Found surface may not be sufficient to induce the plate failure within either the straight plate with the BA28 with the curved plate, CB28 and the 28-inch wheel. The authors continued, however, the introduction of the thermal and mechanical loads produced the emergency braking combined with the mechanical rolling loads produced the considerable higher octahedral shear stress levels in the plate section of the B28 design compared with the CB28 design. This would indicate the B28-inch wheel could develop a greater number of the plate failures than the CB28, depending on the number of the braking cycles, including during normal surface operation, since both wheels design are subjected to essential with the same surface condition with the plate failure if they have occurred only with the B28 design is most likely to be stress, and the CB28 plates are below the threshold necessary to initiate fatigue failures. 523 wheel type. These several types of wheels that used in the railroad industry today. There are varied types according to the material, with mathematical manufacturing design differences. Presently, both wrought steel and cast iron wheels are approved to replace the new car construction. Cast iron wheels are prohibited by interstate chain service after January 1st, 1970. 5231 cast steel wheels. Cast steel wheels are made in one-wear, two-wear, multi-wear design, are furnished in various heat-treated classes of the carbon level according to the AR Specification Association of American Railroads 1973. Cast steel wheels permitted to cool in their molds with complete solidification of the wheel with removed from the mold. Cooled under controlled situated condition of the either both of the after the center of the hub that's removed from the rough bore. All cast steel's wheels receive the heat treatment that produce the desired metallurgical change to provide a favorable stress distribution in the wheels. Except for one class of the cast steel wheels, class unit, all class steel wheels receive the quenching treatment on the treated surface that produce the hardness required by the AR specification. Class A, B, C wheels vary in their carbon content hardness. Raw steel wheels are made of the successful hammering, squeezing operations on hot steel blocks. After final shaping of the wheels, control cool. The raw steel wheels are often heat treated after the initial cooling and either fully and rim quenching only. Perfectly heat treatment is achieved the further modification of the wheel metallurgy, strengthening and hardening of the wheel. R5233 AR specification governing wheel manufacture. The AR specification defined the chemical requirement of the wheel for the carbon content, impurity, the physical requirements of the hardness of the various points on the wheel surface finishing, heart requirements of the wheel classification, incorporating the requirements of the shown figure of the table 5.1. Class U, the untreated minimum carbon content 0.65, maximum 80, 0.8, general surface wherever the untreated wheels are satisfactory. U1 untreated 0.95, minimum 1.2. High speed surface with the surface braking condition, boat loads, moderate wheel. A treated 0.47 to 0.57, B treated 0.57 to 0.67, high speed surface moderate braking conditions with heavier wheel loads. C treated 0.67 to 0.77, light brake conditions with high wheel load surface with heavier brake conditions where tread brakes are employed. L treated 0.47 to heated speed passenger transit. Class A low carbon range of most resistant to thermal cracking. Class C wheels are not subject to thermal cracking and have been improved the wear properties under are heavy low with the Class B wheel to represent the compromise with the Class A and Class C wheels. Worn versus the non-wheel new wheel with the amount of the wheel wear also effective with the thermal capacity of the wheel with in general with the more worn of the wheels higher with the tread temperature with the lower with the thermal capacity of the given level of braking, and this is especially true for the small diameter wheels. And test the performance Western Air Brake Company of the wheels subject to the constant brake horsepower level long period of time up to 60 minutes figure 5.6 compared with the temperature versus the time curve of the new wheels warm with wheels even in these tests or the maximum tread temperature reached for the 40 BHPs was approximately 650 degrees, 600 degrees Fahrenheit with the new wheel versus approximately 720 degrees Fahrenheit warm wheel, an increase of the 120 degrees warm for the warm wheel compared to the new wheel. High temperatures effect with the warm wheels are even more apparent with the small diameter wheels. This is shown figured 5.7. Comparison tread temperature versus the new and worn 28 multi-wear wheels. Our maximum tread temperature for the after 60 minutes with the 40 bhp with the new 28 wheel with approximately 760 Fahrenheit versus the approximately 950 degrees Fahrenheit with the warm wheel with the increase with 190 degrees Fahrenheit with the warm wheel compared with the new wheel. Closely related amount of the wheel wear of the effect of the upon maximum tread temperature of the wear category multi-wear versus one wear of the wheel. This effect can be seen in the figure of the 5/8 minute summary test result to be shown the maximum temperature reached if the wear of the category of the wheels tested. Summary of the wheel temperature test result comparison wear categories. 1 in general, wheel temperature for the higher of the multi-wear wheel temperature for the one when the wheels are new. For the warm wheel, the difference between one wear and multi-wear temperature has become almost negligible. Wheel treaded temperature increases inversely with the wheel diameter and directly with the amount of the wheel wear. 3 when wheels are new, the temperature side of the relationship is more significant multi-wear wheels. However, when the wheels become worn and the effect is negated. R525 brake shoe material alignment of brake shoe material upon until about 1969. Almost all wheels thermal capacity tests are performed on using cast iron brake shoe that held the class arrangement with the Weaver L 1969 report was published in the ASME. The document of the testing of Class C wheel thermal capacity using composition C Cobra brake shoes. Report briefly documented early tests performed at the University of Illinois. The 1950 test was stopped to stimulate with a rapid deceleration rate of 115 miles an hour. The state of simulated wheel load of 20,000 pounds was used in conjunction with the brake shoe force of 20,000 pounds. Each one of the 2 cast iron brake shoes held in the class arrangement. The braking duty represented the total kinetic energy of the 9 million foot-pounds per stop. Result of the test, as some of the authors are, While 5 Class C R wheels, the Class C reintegrated wheel was tested in the man with 3 development thermal cracks after the 1 stop. The remaining of the 2 wheels developed cracks after the 5 stops, 7 stops, respectively. Following shear of the test performed were documented with the large scope of the in 1960 test, simulated with the stops within 31,000 pound wheel load instead of the 20,000 pound load out of the above the 13th test. Result of the test were as follows. The study extremely valuable in that it resulted in a better understanding of the mechanism and theories of the formation of the defect of the development wheels. As a result of the braking heating that wore the extract of the one particularly result of the test with support result obtained in 1950 at the University of Illinois. The average number of the stops required to produce the thermal crack on the CR wheels was 1 stop. In 1968, another test here was connected with the obtaining a direct comparison wheel thermal capacity wheel braked single flange Cobra composition brake shoe with wheels brake from the cast iron shoes. Secondary purpose of the verify the previous test result of the cast metal shoes. For the test, 9 nanometer stops were partially oriented with the top measure line of braking condition of the test parameters and shown in the table 5.2. Test parameter with the cast iron Cobra brake shoe, the comparison test. Test results summarized by the authors after approximately 20 emergency stops were completed. Each wheel number 8925 metal brake shoes began to develop a hairline skin deep thermal crack with abundance of the thermal crack and contributed to each successive stop. Within 37 stops, we were completed on the wheel number 10793 with the flange Cobra brake shoe and dynamometer was being accelerated for the 37th stop on the wheel. The number 8925. A sharp ping was heard. Instead of the producer proceeding with the emergency stop, the machine was stopped without the brakes on the wheel. Within question, examination revealed several thermal crack, extending almost across the complete width of the tread of the wheel. The number 8925 of the test was discontinued at this point. The braking duty dissipating over the 9 million foot-pounds of kinetic energy of the rates over the 137,000 foot-pounds per second without cast iron brake shoes over the 140,000 foot-pounds per second with the Cobra brake shoes and severe any practical surface change of the exceed the previously recommended limit of 125,000 foot-pounds per square second. Another paper presented with the Air Brake Association annual meeting, Berg, Curcia, in 1970, with a further test result of the document, in particular, with the following conclusions were made. Initiation of thermal crack with the dynamometer testing well documented with the alpha trunk proof with the wheel relayed loaded and not necessary for the component of the thermal crack formation. It has been virtually impossible for you with the thrown due for thermal cracks, you with the composition breaks, you the full scale of dynamometers. It's no problem at all that didn't do thermal crack with the cast iron shoes. Under these circumstances, the thermal cracks, one form can be propagated with the dynamometer using either typical brake shoe. Second collision state with above the explained by the examining tread hating pattern. Tread with the cast iron composition brake shoe. The characteristics are compared with the following page in paragraph figure 5.9. Figure 9 character of the uneven heat of the wheel with the cast iron brake shoe. The maximum tread temperature of the composition head shoe more equal to the average of the tread temperature of an equivalent wheel brake with the cast iron brake shoe with at least 110 brake horsepower dissipated emission rate. Difference between a maximum average temperature can be as much as 500%. This temperature differential is one with the primary cause of thermal damage. Brake shoe alignment. Brake shoe misalignment is also known as effective thermal capacity of the wheel. The given level of the brake shoe 4 of the Barrage Garcia 1970 made the following statement: the concurrent statement of the brake shoe alignment, page 95. Not enough of the emphasis of the replay for the importance of having the properly aligned braking rigging. Theory being confirmed by the surface experience. Localized heating has detrimental effect of the performance of the wheel. The British have put forward earlier the year with the suggestion of the rolling contact action of the wheel of the rail produced the beneficial surface of residual compression. Stresses the thermal crack. They claim that it cannot cause the brittle fracture until the penetrated this layer. Therefore, they say that the brake shoe must not be allowed to wander over the front of the rim face lest of the initiate the thermal crack of the area unprotected by preceding rolling contact. It is for the same reason the British railroads have abandoned the use of the land shoes except for the slow speed vehicles. Alright, other considerations. Several of the other considerations must be investigated to estimate wheel thermal capacity of the brief discuss the following. Aerodynamic cooling must be the reach of the performance and investigate wheel thermal capacity did not include the benefiting cooling effect that the wheels would receive the actual train operation. Although some of the research that do positional electrical fans circulate air over the wheel being tested, none of the research resolved quantified the effects of the cooling of the airflow. Closely related to aerodynamic cooling with the ambient air temperature of the environmental through the train is being operated based upon the experimental theoretical results found in research papers. It can be assumed that the most severe wheel temperatures condition would be produced by a severe brake application cycle made on the wheel with the operating within the low ambient temperature. 5262 variation brake force. Although the brake system was designed to produce the uniform brake level on all wheels of the car, experience indicate that it's not always the case because of the binding of the braking misapplied brake shoe. The other cause of the actual brake shoe force can vary substantially from the one wheel to another on the same car. This can cover the higher than normal wheel tread temperature for the more than one wheel within the train. Slid flat wheels. Slid flat wheels are common problems with the present train brake system. It is rare that the freight train can be observed passing without the least of the pair with the slid flat wheels with 1 degree, and other slid flats can be caused by the unreleased hand brakes misapplied with the brake shoe malfunctions like adjuster exemption on high brake pressure settings, binding rate braking, malfunction control valve, probably many of the other cause with regards to the cause of the slid flat wheel. Flooding process itself generates a high localized wheel tread temperature. For empty car with the temperature would be conservatively corrected from the brake force dissipation rate, approximately 100 bhp's wheel summary on wheel. Alright, in summary, because of the process of the estimating wheel thermal capacity must take into account with the shovel variable to discover the previously and because of the individual research observed on a series performed, the type particularly include one of the few variables given in the test here, the difficulty to provide the collective assessment of the thermal capacity of the freight car wheel, subject to tread braking. However, the summary can be made with a concern with the nature of the braking technology, operation, and practice can return with the most benefits from braking while simultaneously maintaining a safe thermal loading. The summary is presented below. Some of the research results, typical brake shoe research has shown the composition brake shoes produce the lower wheel temperature gradients, equivalent type of the horsepower dissipation rate, but then they produce the cast iron shoe for the two reasons they have then put forth explaining this result. The tread temperature distribution across the tread in the axle direction is the most uniform with the composition brake shoe. Then the cast iron shoe with the cast iron shoe tends to form rings on the bands extremely high temperature on the treads, which are local hotspots. More uniform temperature of the distribution produced by composition brake shoe because of the smaller temperature of the gradient in the radial direction along lower wheel stresses. Furthermore, save the result of the one test here with the Bristol Kerosene of the 1970 been virtually impossible to induce thermal crack of the wheel with the composition brake shoe with the full scale of dynamometer. Although one cracks are formed and some other means of the cracks can be propagated with the composition shoe, should be further noted that instead of the test of the the dynamometer with the composition shoe, the most cases of work consumed before the wheel thermal cracks occurred. Wheel diameter cross-sectional shape of the test result to indicate a large diameter wheel with exhibited lower tread temperature given the level of the braking, the small diameter wheel with a new multi-wear wheel tread temperature is produced at 40-inch wheel with a wear much is 25% lower than the temperature produced at 28-inch wheel. Although this effect was not seen at the warm wheel, the theoretical analysis of the 28-inch wheel indicated that under combined physical thermal loads, curved plate 28-inch wheel exhibited substantial reduced wheel stress compared with the two straight plate with the 20-inch wheel, with the result was substantiated by the fact of the wheel plate failure for the selected freight train operation curve exclusive of the straight plate wheels. 5313 typical brake rigging avoid the extreme variation of the brake level of the individual wheel of the freight car. Brake rigging must be capable of providing a uniform balanced brake shoe force on each wheel. Almost important in selection of the brake rigging to provide the proper brake shoe alignment. Wheel metallurgy, although the metallurgy contains some of the typically selected based on the under consideration, particularly shelling and spaling, where characteristics of the standpoint of the wheel thermal capacity, wheel with low carbon content, most resistant to the thermal cracking, brake application cycles, speed with the great operation temperature, shock with effects that have been demonstrated to be damaged within the wheel, if they have the severe brake application over a long time period with the train operation should be managed. Such cycle braking of the severe nature should be required so that the descending grade train speeds are limited to the safe level of horsepower dissipation. See figure 510. Safe energy dissipation rate. The purpose of the above summary was present favorable conditions to be obtained. The freight car wheel to use the out-tread braking techniques. Safe energy dissipation for the freight car wheel to have an tentative to determine the 33-inch Class U wheel to Bennett Wet and Kipp in 1975. Research were performed at University of Illinois, sponsored with Griffin Wheel Company. Tentative to safety energy dissipation versus the time curve of the shown in figure 511 should be noted with if the results do not include physical mechanical wheel loads that would be experienced in services. Safe energy. Or the tentative safe energy dissipation rate curve assumption is systematically approach of the 40 bhp level of the time by substantially greater than 40 bhp with a short time period. Previous discussion research of the brake system professionally have generally revealed with the curve presented with the figure 511 conservative to be conservative. This is especially true with the guidelines presented previously or filed, and then the appendix is the glossary of terms, and this concludes the Brake System Design Optimization Volume 2 Supplemental Data Report Number FRA-ORD 7822, April 1981, April Final Report